All right. So I know you're watching this video because you hope to do well on your Unit 1 exam in astronomy. So know that I want you to do well too. So there'll be 3 parts. The first part will be multiple choice, MC for multiple choice. My thing's not working. The second part will be vocab, fill in the blank. And the third part will be short answer. And all of the tests this semester will be like that. So what I've done basically is to bring in PowerPoint slides that correspond with what the you're going to see a test question over. So for instance, on your review sheet it said branches of science. So of course astronomy here is most like a physical science, not a biological science or a social science. So probably some sort of question along those lines. This is just to kind of remind you of something we talked about earlier this semester for this test. Scientific method, it's a classic. So, of course, scientific method has some key terms. Hypothesis is sometimes called a best guess. Then we do experimentation. We do this a lot, and we have several slides to kind of show that. Now, if our hypothesis continues to pass the tests of experiments, then it can be elevated to a theory. So kind of know those terms. Pseudoscience. Pseudoscience is something that kind of sounds like a science. Ology is the study of. So we have these kind of pseudosciences here: astrology, zyptozoology, numerology, and ufology. So they're not a real science, but they kind of sound like a science. So speaking of science, you're going to have a question over what are the hallmarks of science. And they're over here. I don't know if you can kind of see this. Basically, it seeks to explain observations, but it has to be based upon natural causes. We use observations are used in the field of science. Notice that the explanation needs to be as simple as possible. That's called the KISS principle. And then down here, science needs to be testable. So those sort of things. And that's it for part 1A. We go to part 1B, and like this. Okay, I'm going to ask you, we talked about different distances in astronomy. We'll keep talking about different distances, but especially with our solar system, an astronomical unit, of course, is the distance between the Earth and the Sun. The average distance, we know it varies a little bit. Then I have, on my notes here, you're going to need to be able to pack up numbers in scientific notation. I haven't decided pack or unpack or recognize, I'm not sure. But remember, if it's a big number like this, that's going to be times 10 raised to a positive power. And if it's a smaller number like this, it's going to be times 10 raised to a negative power. So I've got some examples, and we did some examples in class, especially the big ones in astronomy is what we're worried about. Of course, you guys would tell me the decimals here with the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9. Move it 10 places. And so that's times 10 to the 10th, and I get a number of 1.23. So that is that number packed up in scientific notation. So let me know if you have any questions about that. Then I have on my notes a number of galaxies in the observable universe. So I think this would probably be a multiple choice question. I just think that's amazing. Of course, you would tell me we're in the Milky Way galaxy. And there, in the observable universe, you're talking about 2 trillion other galaxies of stars. I just think that's totally amazing. Let's see, viewing the Milky Way in the nighttime sky. So we don't, if the darker skies, you might see kind of something sort of wispy like this. Okay, you are actually looking into the plane of the Milky Way galaxy. It's hard for me to kind of do this on a slide. But you're like, we're in a frisbee, the Milky Way galaxy. The sun is going around the center of the Milky Way galaxy, and you're looking into kind of the heart of the Milky Way galaxy. I don't know if I... All right, let's see. History of our universe in 1 year looks like this. Just such a cool sort of thing. So I'll put BB here for Big Bang. And then we are here, just getting ready to bring in the new year. And actually, humans did not appear until, let's see, the evening of December 31st. Isn't that just amazing? And all of these other things have gone before us. So we'll be talking a little more about that later too. All right. So now on to the next part. Let's see. Just zipping along. Part 1, 2A. I have a question, or we'll have a question on there about revolution and rotation of the Earth. Get your R's. Make sure you got your R's figured out. So the Earth spins or rotates on its axis once every 24 hours. It used to spin a lot faster, didn't it? And the Earth revolves or orbits about the sun. And of course, that takes 1 year. And there's another thing coming up, that the Earth's axis of rotation is tilted 23.5 degrees. So you want to know that. Let's see, movement of the stars throughout the course of the night. Oh, did I miss that one? Oh, here it is. Kind of out of order here. So motion of the stars throughout the course of the night. So stars will appear to go counterclockwise around the star Polaris. Okay, there is no South Pole star. Of course, if you're in the southern hemisphere, you can't necessarily see Polaris, can you? But anyway, so Polaris is the North Star, and the north axis of rotation is pointed at Polaris. So the stars will go counterclockwise around Polaris because the Earth is spinning on its axis. Next one, seeing different stars at different times of the year. Well, let me go back. This one's parallax. Parallax is remember where you held your finger out in front of your nose? Basically, and close one eye and then the other eye. And then as you took your finger and moved it out away from you, you saw less movement of your finger as you closed one eye and the other eye. That movement that you saw of your finger, that's the object that's relatively near you against the background. And then the parallax was you were kind of changing your point of view. So, and we actually went outside and did a little experiment like that too, didn't we? I have on here seeing different stars at different times of the year, and this is kind of what I'm after. So you can see the Earth orbiting counterclockwise, right, the sun, and you can see, for instance, if we are over here, June, notice at nighttime we're going to see Scorpius and Ophiuchus. Okay, during the daytime, the sun is appearing to go through the constellation Taurus, which of course we cannot see those stars in the daytime. Now, if we go over here, let's put you 6 months later. Okay, if the Earth is here, notice we are going to see Taurus at night, but we're not going to see Scorpius or Ophiuchus. Let's see, parallax, seeing different stars at different, celestial sphere hopefully should be next. Yep, celestial sphere, so that's that ghostly looking sort of a sphere, hollow sphere with the Earth in the center. So this blue fuzz, that's your celestial sphere, and those white dots, of course, are stars. So it's a model of kind of how the stars stay fixed, and the Earth will spin around on this axis of rotation. Let's see. Local sky, altitude, and zenith. So here we go. Nice to be able to kind of orient yourself as to what you're looking at. And so you can see this person standing here, and if she's looking at the sun here, it looks like the angle that the sun makes with the horizon is 60 degrees, and that's called the altitude of the sun. Another thing on here is anytime a spot directly above the observer is called the zenith point. All right. Something that's kind of helpful when you're trying to describe to somebody what's up there in the sky is what we call angular distance. And so what you do is, like this person's doing, you hold out your hand, and as you do so, your knuckles here would be about 10 degrees, and the span of from your thumb to your pinky would be about 20 degrees. Your finger itself would be 1 degree. So that's the size of an object, or kind of what we call the angular distance. So as this works out, the stars in the bowl of the Big Dipper are about 5 degrees. So that's what, about half of the span of your hand. The moon, the disk of the moon is about a half a degree. So if you extend your hand, you're looking at what? About a half of your finger. All right. Then I got motion of stars viewed from the North Pole. Okay, this is where we say that the stars throughout the course of a night will appear to orbit counterclockwise around the star Polaris. And so if you are a polar bear at the North Pole, the North Star Polaris is going to be at your zenith. So actually, as you look down, you're going to see a circle getting bigger and bigger and bigger. So you're going to actually see a circle on the horizon. So that's kind of what I'm after. There's going to be a test question about that particular kind of how these star trails would look if you kind of plot them throughout the course of a night. Let's see. Constellations along the ecliptic. Okay, it's like deja vu. We did this before, didn't we? So, I want to say this, I don't know much about astrology, but, you have the signs of the zodiac. And so, as it turns out, all of these stars along the ecliptic, I don't have the ecliptic as a term, do I? And I kept telling you I would. Remember what the ecliptic is? It's called the plane of the ecliptic, and it holds the planets as they orbit the sun. So these constellations along the ecliptic are going to be the constellations of the zodiac. So I hope that works for you. Okay, now on to the next part. We're up to part 2b. I have a little note here. There'll be a question about prime meridian. So let's see, how's this work? So these lines of longitude go like this. That's lines of longitude. And you need to have a starting point. Lines of latitude have a starting point. That's the equator. So lines of longitude have a starting point. It's called the prime meridian. So that would be 0 degrees. And then it goes west and east of the prime meridian, and it meets back here at what we call the international date line. I think I have a picture of that coming up. Okay. So the longitude starts, and it sweeps around and back here. So here you're looking at 180 degrees west and 180 degrees east. So I hope that makes sense. Let's take a look at that. Let's see, Earth's tilted axis of rotation. I think I mentioned it before. It's 23.5 degrees, and the cool thing is that it keeps its tilt in the same kind of configuration as it orbits the sun, all pointing up here to the star Polaris. So it's pretty cool. Let's see. So then Earth seasons. Earth seasons. Good. It's down here. Earth seasons actually then give us two things. One is kind of the directness of the rays, and I talked in class, something I bet you've already noticed is that in the summertime at noon, you're going to have the sun's going to be high up in the sky. And the wintertime at noon, the sun's going to be kind of low at the sky, even though it's at noon. And that has to do with the Earth's tilted axis of rotation and how the tilt is relative to the sun. So because of that, when the sun is high, the rays of the sun are basically spread over a smaller area, 1.04 meters squared, versus when the sun is low in the sky at noon, or actually all day in the winter, and that same amount shaft of light has to spread 2.24 meters squared. The other thing about the sun, and as well, I shouldn't say about our seasons as the Earth orbits the sun, is we definitely have different hours of daylight. So I've kind of got some extremes here, and I just picked on, if you're at let's see, north of the Arctic Circle, I don't know if I got that right or not, but Yeah, that would work. If you're near, just say near the North Pole, at the winter solstice, you're going to have 0 hours of daylight, and at the summer solstice, you're going to have 24 hours of daylight. So it's the hours daylight and the directness of the sun that gives us basically then our seasons. All right. On to the next part 1-3. And we start out with a question about what are the conditions for us that we would actually see see parallax in the stars. So honestly, we usually think of the stars as making a pattern, and that pattern is fixed. Like the Big Dipper is going to be the Big Dipper, whether it's in the springtime or the fall time or the summertime or the wintertime. But if a star is relatively close to us, and this is an example of a nearby star, okay, we talked about this, that actually parallax will apply when we're 6 months apart, okay, and we look at that star, and in July, that star is going to appear actually kind of over here-ish, okay, and then in January, since that star is relatively close, it's going to appear here-ish against the background stars. The background stars here are white, their nearby star is yellow. So we do see it has to do with the tilted axis of rotation. Oh, I wonder if Earth orbits the sun. The next one, historically, what have we used the observation of the sky for? And I have a couple slides here. Cultures have used the motions of the moon, the sun, the planets, and which star systems they see, or which constellations they see, to understand the time of day and the year, track the cycles of the moon. They observed the planets and the stars, and they definitely created their own observational places that were key to what they saw. So here they would use the how the crescent of the moon was configured to understand when to plant because of what the ring was doing. Here we see they're seeing time over here. Stonehenge would actually is set up so that the shadows at the solstices and equinoxes, I want to say, give a particular shadow. And then over here, we've got some neat things. Again, this goes back a long time, but this is a sun dagger where at on the summer solstice, because of how this kind of bullseye back here is and the slit in the rock, that slit lines up with the middle. This is an amazing feat of architecture here with Pikachu Indians to honor the important times of the year. And then this is probably one of my favorite. Can you kind of see those little knob things would be stars, and so navigators would line those up with the stars to understand what direction they were moving. So those slides are all about the conditions in which, those are the second one. Those are about historically observations that the sky has been used for. Okay, we move on to the heliocentric versus geocentric model. So heliocentric means sun-centered and geocentric means earth-centered. And so they used to think like this. This would be the geocentric. And in the geocentric model, the Earth is in the center, and the stars orbit the Earth. I know it sounds weird. The sun orbits the Earth, and the other planets orbit the Earth. That's so bizarre. But then the heliocentric model is, I'll just make it right here. And the heliocentric model, which is the real deal, that's the sun. And of course we have the planets orbiting the sun. So this is heliocentric. Helio meaning sun. Centric meaning center. Okay. What else we got? Retrograde motion of the planets. All right, so this is Mars, actually, where Mars is against background stars. Here, this is direct motion. Let's see if I got this right. Direct motion to me looks like this. Okay, so it's supposed to go like that. That's direct motion. And as see, Mars is going faster than the Mars is going slower than the Earth. As the Earth overtakes Mars, Mars will appear to go backwards. So this is retro, and this is direct. And the reason, like I said, that we see that has to do with the Earth, let's see, yeah, the Earth overtakes the slower moving planet, in this case Mars. Now that will work for you, but I really think, as I think about it, we can also see retrograde motion for the inner planets, which would be going faster than the Earth. I don't know. I have to think about that. Okay. Next. So there's going to be a question on Aristarchus was even before Copernicus. There it is. Okay. Aristarchus was also heliocentric model. Okay. But, and where's Ptolemy? Goodness gracious. Because I have Ptolemy listed here. Well, let me see. I gotta check this out. It's gonna drive me nuts. There we go. There's Ptolemy. This one's Ptolemy, geocentric model. All right. Goodness gracious. So those scientists kind of know a little scientists that we talked about. So I have a little bit about most of the scientists anyway. So know a little bit about Copernicus. Copernicus was the guy who actually, he was the one who started the momentum towards the heliocentric model, Copernicus. Brahe came after Copernicus, is the way I think of it. Brahe had all sorts of measurements, and that's his fancy measurement tool, measurements. Okay, and then, but he still needed help understanding the measurements that he took, and so Kepler, he studied the measurements of Brahe. That's what I think of it. And Kepler, of course, came up with 3 laws of planetary motion, which we're going to take a look at here in a minute. Who else I got? Galileo, he was definitely in the mix, definitely along with the heliocentric model. And looks like, I can't remember. I'm looking at, no? Okay. Well, I don't think I have any question about Galileo. I thought about it. Newton then actually came up with some, he was a mathematician and a scientist, and so he came up with general laws of motion. Okay, the one thing I don't have on here is Aristarchus. Oh, where is Aristarchus? Oh my goodness. Well, Aristarchus, you're just going to have to, maybe do I have Ptolemy up here? No, I don't. Ugh. Well, you're just going to have to know. Remember Ptolemy? He was actually the geocentric model. Yeah, and I thought, goodness. I bet I had, hang on, have a sense of them. Kepler's 3 laws of planetary motion look like this. His first law is actually the shape of the orbit of the planets. Remember, those are called, that shape's called an ellipse. Kepler's law, remember Kepler's laws only deal with planets, is this one right here. And it says basically, this is one where it went, so basically it moves fastest here. And this is at perihelion, I promise. I know I got that wrong a few times in class. And this is at aphelion. Okay, so it goes slower here. So it's kind of confusing keeping his second law and his third law straight, but his second law deals with just one planet orbit. Okay? Now, his third law says that, and forget all this blada blada, but if I go down here, this is the order of the planets where this is the closest, of course, you would tell me. Mercury's closest and Pluto's the furthest object, not a dwarf planet, but anyway. And here is how long it takes them to orbit the sun. So not only is their orbit larger, but they go slower in their orbits. So I'll go like this, slower. Okay, so according to Kepler's third law, the farther you are from the sun, the slower you move in your orbit. All right, I'm flipping over my page now. You can flip over your page too. We are on to part 1-4. And that's Newton's 3 laws of motion. This first one is F is equal to ma. Force is equal to mass times acceleration. So that means that the stronger the force, the stronger the acceleration. His second law goes like, oh, did I miss his law? For, where's this? Oh, wait. First law, second law. Oh, that's the second law. Sorry, second law is force equal mass times acceleration. His first law basically says that an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an outside force. Now, of course, so we could kick this. This is my foot kicking this. That would be my force to make that move. Or we could start something moving and it's going to slow down because the force of gravity. So for first law, objects will stay in motion or stay at rest unless acted upon by an outside force. Okay. Second law is F is equal to ma. Third law is for every action there is an opposite and equal reaction. So if we push off this way, we're actually pushing a force that way, and that's kind of what's happening with the space shuttle there. Okay. All right. Newton's law of gravity is this. He said that the force of gravity is equal to some constant times the two masses that are being pulled together divided by the distance over which they are separated. So get a kind of a double check, make sure you kind of get a sense for that. And we have on Earth any object, how do I say, any planet or moon will have a pull of an object perhaps to the surface as it's dropped. Our acceleration that objects feel due to the force of gravity is 10 meters per every second. It falls, 10 meters per second faster for every second it falls. So 10 meters per second squared. So in other words, we said that the first second something falls, it's going to be going 10 meters per second when they look at it. You let it go ahead and fall another second, and now it's going to be going 20. If we were to go t is equal to 3 seconds, guess what? Its velocity would be about 30 meters per second. So it kind of picks up speed 10 meters per second for every second it falls. All right. Now what do we got? Basic structure of an atom. All right. Aw, you guys did good on this, so just kind of remember kind of how this works. This is what we call the nucleus. You can't see it here. That's the nucleus. And here we have the protons and the neutrons, and this buzz out here are the electrons. So I think that's kind of what I'm after. Yeah, that'd be the basic structure. Let's see. Then I've got thermal energy. So thermal energy is measuring basically how fast objects are going. So here we've got two boxes, and you can if you use the length of the arrow for how fast it's going, you can tell this is the higher temperature because they're buzzing faster. This is the lower temperature. So that's kind of what I'm after there. And actually, all matter has a certain amount of motion, and motion is associated with what we call KE, or kinetic energy. Let's see, what did I have next? Oh yeah, and then I did want you guys to make sure we're on track with regard to the temperature scales. So we have, of course, we're used to looking at our temperature in Fahrenheit. So water freezes at 32 degrees Fahrenheit. But these are both metric, the other ones. Fahrenheit is an English system. So Celsius is the metric, and actually Kelvin, indicated by the letter K, is also a metric. And so the thing there is, let's see, yeah, absolute temperature, absolute zero. The thing is, I said that all matter has motion, but at a temperature of 0 Kelvin, okay, then the motion stops. All motion stops, and that's an amazing thing to consider. I know it doesn't look like the atoms in this table are moving, but they are. Okay, so, but at absolute zero, they would stop moving. Okay, think about that. All right, so on to part 1.6 here. Okay, so supermoon, and they both have to do with full moons. So supermoon is when the moon's going to look especially big because it's near us. Okay, I don't have it on the. It's not like a term I guess I'm going to ask you this semester, but perigee is when the moon is relatively close to the Earth. And so if it's also close to the Earth and it's full phase, we call that a supermoon. If it's full moon and it's at farthest from the Earth, that's what we call a mini moon. So those are kind of fun. Lunar phases. So I've got them listed here. You're going to need to know the eight lunar phases. We talked about the major phases, so new moon, first quarter, full, and last quarter, and then I'll go back to new. But we have these in-betweens, like we have the crescents that are less than a quarter. Then we have gibbous that are actually more than a quarter. So, and these are both waxing because it's getting fuller. And then after the full moon, it goes to more than a quarter gibbous. And then it'll be a crescent after last quarter, and it's waning in those cases. So know those phases. Let's see, what else we got? Okay, I'm reading my notes here. Moon's orbit and Earth's rotation on its axis. So there's a few different ways to do this. Actually, you guys, I think, did this in lab too, where this orb here is the Earth, okay, and this gal here is the moon. And you can see that if actually she did not rotate, no rotation, then we would see, or we on Earth would see the front of her here, and we would see the back of her here, okay? But as it turns out, we only see one side of the moon. We have a near side of the moon, and that's because the moon rotates, okay? So you can see her actually kind of spinning around just a little bit and a little bit and a little bit. So we only see which side of her? So we only see the front side of her. And specifically, so the front side of her would be the near side, sorry, this looks so sloppy, and the back side of her would be the far side. Yep. And specifically, it takes about, is it 29 and a half days, or about 28 days, about a month, to complete for the moon to orbit the Earth once and for the moon to spin on its axis once. Okay, we call that synchronous rotation, which I don't think, is that on there? I don't know. I guess it could be. It seemed like it could be fair game to me. Okay, so near side versus far side. I feel like I've kind of covered that, but I've kind of covered that. So Earth's tides are caused by the moon. So here we see the moon here, and we kind of see the moon, of course, is going to orbit the Earth, and you see kind of this bulge of the Earth's atmosphere, in a sense, and actually also water being lifted off. And it's lifted off also directly on the other side of Earth from that bulge. So it has two bulges. Here's a bulge here and a bulge here. And so you figure it, if this part of the Earth is going to be over here 12 hours later. So that's why every 12 hours these oceans, our oceans, experience high tides. All right. Okay. We have super moon and mini moon. Oops. Wonder where my stuff went. Let's go on to eclipses. So I only have one slide for both types of eclipses. I hope that's okay with you. This actually, the thing that's getting blocked out is the thing that's the eclipse. So this is showing you a solar eclipse. Okay, and a solar eclipse can only happen when the new moon phase. Okay, now the lunar eclipse, then it's not shown here, but if we figure the moon scoots around over here, and if the moon goes through the Earth's shadow, can you see where we can have a lunar eclipse over here? And this would be, okay, so I hope that works for you. Then on to the next part. So part 1-7. So you're going to want to know generally the steps that we got our moon. I just think that's so cool that our moon is a little piece of the Earth. And so here we have an impactor striking the Earth. The impactor went about its business, but in the meantime, part of the Earth splashed off and kind of went here and inserted into Earth's orbit, kind of solidified. And that, my friends, is the moon, which was a piece of the Earth. Isn't that kind of cool? All right. Then I have listed Mare versus Highlands. So hopefully you would tell me that the Mare are dark regions and the Highlands are the light regions. The Mare are the relatively young and the Highlands are relatively old rocks. Let's see, regolith. Regolith is lunar soil, so you can kind of see a picture of a footprint in regolith there. Features of a crater. So here I have, craters often have that central peak, I call the belly button. The terrace sides and the ejecta blanket are kind of that amount thrown out here. This guy is Tycho. You know, craters are named, and you can kind of see the ejecta blanket out here. Of course, I can't see the central peak or the terrace. Let's see if I can see here. Oh, that's okay. That's a central peak. Not bad. And terraced edges would be kind of around here. All right. On to, oh, I guess I did have another slide. Sometimes my slides are repeating slides. Here again, I kind of talk about the central peaks, the terrace sides, and that, the ejecta blanket. The color can indicate how long it's been there. Okay. Now on to part 1-8A, a full moon phase. And it looks like this, where we first talked about asteroids and meteoroids. So we usually think of the asteroid belt is where asteroids are, and of course that's between Mars and Jupiter. But there are a couple other places. So one is if we pick on Jupiter, okay, we can look and actually find Jupiter in its orbit about the sun. It's all about counterclockwise, and it's got some, you can't see this, but it's got some Trojan asteroids right here, and it's got some kind of in front of it, and it's got what we call, what do we call those guys? The Greek asteroids. Well, this says in front and behind. To me, the Greek asteroids kind of look behind, and the Trojans look in front, but that's okay. All right. Then the last one are the wild children, the Apollo asteroids, which actually all the stuff in our solar system that's part of the solar system has to orbit the sun. So these would be our kind of wild children that go kind of maybe like this, where if I'm not sure, probably the blue line in here is Earth's orbit. Can you see where the Apollo asteroids are the ones that cross Earth's orbital path? And so those are the ones that we're most concerned about. Let's see. We're getting close. All right, I wanted you to know the difference between the M's. Okay, meteoroid, think of like asteroid. Meteoroid is just a little smaller than an asteroid. It's outer space. A meteor is actually as the meteoroid falls through the earth and creates that streak of light, so it's pretty fast. A meteorite then is that a piece of the meteoroid has survived its trip through the Earth's atmosphere and you can pick it up. So this actually is a meteorite. Big meteorite, but it's a meteorite. That's what you need to know about that. And then on to the next part, 1.8b, comets. So comets are kind of like asteroids and meteoroids. They're leftover stuff that didn't turn into a planet, but they have an icy component, unlike asteroids and meteoroids. The two main locations for comets are in the Kuiper Belt. Okay, so the Kuiper Belt is in the plane of the ecliptic. So this is kind of, you see Neptune's orbit in blue, and you can kind of see these kind of fuzzy regions. That's the Kuiper Belt. The Oort cloud is amazing. So this stuff out here, that's the Oort cloud. So the Oort cloud is spherical with the sun in the center. Let's see. Demotion of Pluto, right? So as it turns out, Pluto, if you look at the true planets in our solar system, you figure beginning with Jupiter, Saturn, Uranus, and Neptune, they are these gas giants, and then you get to Pluto. And Pluto is definitely much more like a comet than actually it is a planet. So the criteria that Pluto failed was it failed to clear its orbit of debris. So this is just to say that as Pluto orbits the sun, this is P for Pluto, it's got crumblies there, actually fellow comet-like material that it did not make part of itself as it was forming. So I hope that works for you. Meteor shower then. So a meteor shower we couldn't really talk about until we finished talking about comets. So a comet, every time a comet gets close to the sun, it starts to fizz. And as it fizzes, it leaves some of its material behind. And so what happens is for a meteor shower, the Earth passes into some comet poop, comet guts, that was left behind in that trail where the comet orbits the sun. So, yeah. Usually without a meteor shower, you can see one meteor for every about 10 minutes. But if you have a meteor shower going on, sometimes you can see up to 75 to 80 meteors. Could that be right? Per minute, I don't know. Or hour, I don't know. But a lot more than one per 10 minutes. Okay, so meteor showers are caused by the Earth passing into debris comet. Just a few more, like we have here. I have in my notes Pluto is most like, and hopefully you would tell me that Pluto is most like a comet. Okay, then it is a planet. And then I have in my notes who and how was Pluto discovered. So this is who discovered Pluto. Okay, so Clyde Tombaugh. In our last lecture on Monday, we'll be talking about this. And then how did he discover Pluto? And he discovered Pluto by patience. Oh my gosh. He basically, and it's hard for me to see, I see these stars here. He compared these pictures and he actually saw Pluto move. Okay. So there you go. That is amazing. All right. So then the only other thing I see on the sheet I'm looking at for you guys is there are some video questions that you wrote down. It says you need to know two, and that's what I mean. You need to know two. You wrote one, and you need to be able to kind of answer one of the other ones that was written. All right, let me know if you have any questions.